Welcome all. Good morning. Greetings from Team Bob the Builder. I'm Shranik Bora, Technical Event Head of Bob the Builder 2.0. So today's webinar is just focused on the competition, and it will exactly teach you how to design and optimize the structure of a transmission tower or a steel tower, which is a lattice tower. So today's particular session is a recorded video for all the participants who are going to view this video online. This video will be streamed online at the same time when my workshop will begin at here in campus. So don't worry, my workshop content and the content of this recorded video will be exactly same. I'll try my best to keep all those things as same as possible. And at the same time, this particular webinar or a recorded video will be focused for online participants. Obviously, offline participants can also see this video after the workshop is over. So for the online participants, I'll suggest you to go through our playlist. That is a toolkit for the competition in which there are 3 sessions for Staad and the last is the final webinar session. So this particular session which I'm conducting right now is focused for all those participants who have done something, who have practiced Staad and they know the basic things about Staad and steel structure. So I'm going to go through some of the things like geometry, assigning property, creating some different geometry by translational repeat, rotational repeat, etc. I'm going to go through these things a little quickly, but I'm definitely sure that you people will be able to understand if you have gone through my previous videos, and also all those people who have done my homework assignment. And I'm really glad that a lot of people have submitted their homework assignment. And they have done some excellent work. So keep on doing excellent work. I really, appreciate your efforts. So let's begin the session. Okay, there are a few announcements before beginning the session. Our final problem statement will be released today, which is 24th of February at 2 p.m. sharp. And for the deadline for the submission of your final design is 7 a.m. sharp on 25th of February, which is tomorrow. And there are some other things regarding some scoring system. I'll just giving you a brief overview about scoring system before beginning to the session. Obviously, the scoring system will be described nicely in our problem statement. But before going further, I'll just tell you there are total 250 points, out of which 15 points are dedicated to homework. And you can get maximum 15 points in homework. According to the quality of the homework and accuracy of the homework, you'll be assigned marks for each assignment. And at the same time, you have 5 marks for a iterative design process. Okay, so all those who have gone through my webinar till now or the final webinar, today on 24th, you have to submit your I will be giving you a problem statement on 2 p.m. and after that you will be submitting the file of your initial model. See, you're going to obviously create 2, 3, 4 or many models, but I need your stat file of your initial model before 7 p.m. So, or 7, I think it's 7:30 p.m. 7:30 p.m. You could check those things in problem statement. That will be better. Exact timings. I think it's around 7 p.m. on 24th. And according to that, after you submit the models, we'll be creating an Excel sheet by viewing your output files, and we'll be publishing the results of your models. So don't worry, those results will be anonymous. We'll be just putting up some team numbers randomly, and we'll be putting up the values of your takeoff values. Takeoff values means self-weight value of your structure. And we'll be assigning 5 points to this initial model submission. So this should be done within the time, otherwise you won't get the 5 points. And at the same time, you're getting those who haven't submitted the homework assignments till 23rd, which is yesterday. We have a chance for you people. You can submit your assignments till today, which is 24th, till 10:30 p.m. And but there is some penalties. You can at max get 2.5 points for each assignment. That will be 7.5 points for total all three homework assignments. So those are some things. And so I was explaining you the point system. So 15 points for that homework, 5 points for initial model submission, which is today, and okay, 225 points are given to the main final model submission, in which to the distribution of 225 marks exactly will be provided in problem statement. And there is one more submission. After you're done with your problem final design, your testing will be done, and you have a deadline. You need to do a task, and I have assigned 5 points to that task also. The task is very simple. You need to post your pic of the model after after doing the final submission. While we'll start our testing at 9 a.m. on 25th. So after 9 a.m., you could post your model's pic on our FB page, which is Bob the Builder 2.0 FB page, and before 11:30 p.m. 11:30 a.m. on 25th. So you will get 5 points for a post in which you will be sharing your model's pic. So this is the distribution of all 250 marks. So 15 marks for homework assignment, 5 points for initial model submission, 225 points for final model submission, and 5 points for Facebook post. So that's it. So now we will begin with the session. Today we are going to solve a somewhat similar sample problem statement. Okay, so I'm opening my Staad window. I hope my voice is quite clear. Okay. Then I'm going to a new project. Okay. So now onwards, please don't forget this point. Whatever structure you're going to design for this particular competition should be a truss structure. So always choose truss. Make sure your new units are proper, meter and kilonewton. Just put next. I'm just going to structure wizard. What I'll do is I will go to add beam, click on finish. Okay, I will edit this grid to XZ, no, XZ, okay. But still, I don't need this grid. What I'm going to do is I'm going to create a geometry of a tower, a tapered tower, which is, don't consider it as a transmission tower, but it should be a lattice tower, steel tower or a steel chimney, you could call it as. So what I'm going to do is, but before creating the geometry, I'm going to apply some kind of load. So make sure that for this particular competition, y-axis, if you consider some kind of geometry, so that every cross section of the geometry have its center of mass or CG. So y-axis should pass through that all center of gravity of every cross section of the figure. I'll be explaining this point. I'm just closing this grid first. Wait a minute. Then I'm putting some coordinates. I wish to go with a larger section, so I'm going with 2, 0, 2. I'm just creating a square of 4 by 4, 4 meters side, and such that origin should be at the center of the square. So I'm just putting some coordinates. 2, 0, -2, enter. Then we are putting -2, 0, 2, enter. -2, 0, minus 2. So this is it. This is a square and we will put the origin again then 0, comma 0, comma. Okay. So you could see origin at the center. Now we'll go on adding beams. Okay, great. Now what we'll do is we will have a smaller cross section at the top of this. So for that, since we have considered 4 by 4 side, we are going to consider 1 by 1 at the top, and we are considering height of the tower as 12 meters. Remember, height of the tower is 12 meters. So we are going to put it as, we are putting 1 by 1 now. So 0.5 comma 0 comma 0.5. But wait a minute, y coordinate should be 12, don't forget that. Similarly, come down, put 0.5 comma 12 comma minus 0.5, enter, and put minus 0.5 comma 12 comma 0.5, enter. I think I don't know. Okay, wait a minute. Last coordinate no, minus 0.5 comma 12 comma minus 0.5. That's it. So these are the 4 coordinates at the top. So as that this makes up for the square of size 1 meter. So join them. Okay, now join the respective nodes. So total height of the structure is 12 meters. I hope this is quite easy for you people, because a lot of people from your side has done homework assignment 3, which was really a challenging job. So great work, guys. So for those who have done homework assignment 3, this is a piece of cake. Okay, now we'll do it. We're going to divide this entire 12 meters in 3 parts. So we'll insert 2 nodes, say add endpoints. Okay, add 2 points. Okay, add endpoints. Okay, done. Add endpoints. Okay, so this is a geometry we have created. Now what we'll do is we will create those nodes also. I'm just doing it. Okay, I'm just adding beams. Okay, I'm just adding beams. After that, what I'm going to do is I'm creating a very, very simple geometry. Now I could repeat this geometry, but how to repeat it particularly? I will not go, go on circular repeating it. I will show you just a glimpse of that. Go to member cursor, I'm selecting the member and say you're going to circular repeat about y-axis in 360 4 times, 4 number steps, click OK. And you see this is repeated. But I don't want such a structure, right? So I'll put Control Z. What I want is, I want to create a mirror repeat somewhere. Okay. So that's why I'm drawing nodes, the members manually, so that it will not be a havoc kind of situation. And it will give you exact geometry which I'm looking for. Can you see that? This is the geometry which I was looking for. Done. Now what we'll do is, since there are some loading constraints which you will understand when we'll go to the loading, I'll just adding few beams here so that it will be easier for the loading purposes. No, we don't have a load here. Okay, I'm adding load here also. Nodes, members. I'm just adding diagonal members. That's it. Okay, now what I'll do is I will add a node at intersection of the diagonals. I'm just doing it very quickly. I'm putting Control A, Control A. In Control A, I'll put geometry. Say intersect selected members. It will intersect. Okay, done. So the members got selected. Great. So I'm putting the nodes at the intersection also. Great. So okay. So basically our geometry is ready. Now we'll go to general and assign some properties. Would you like to see the geometry again? Okay, so basically your geometry is ready. Now we'll go to general, create property, go to section database. Remember that you're only allowed to use sections from Indian section database for this competition. I'm choosing angle section. I'm choosing a little heavier angle section, 65 by 6. Click on add, close. And I'm assigning this one particular section to the entire geometry. Obviously, you must have learned how to create groups, how to create different type of members, and how to assign those particular sections to the particular assigned groups. But I think that's a part which I'm not focusing today. I'm focusing on much on how to optimize your design. So we can just go as fast as we can, and it will be easier for you also. So just go assign to view, assign. Okay. So the geometry, now you can see in 3D rendered view, you can see here. Okay, I'll show you how to. Again, I'll go to geometry. General. You could see here, there's some factors. Okay. Okay. So we assigned the geometry, we have created geometry. Now we assign the properties as well. Now I will show you something called beta angle. So what is a beta angle? Beta angle is basically for the orientation of steel members. So you could orient the steel member according to the beta angle. So basically it's a rotation about its own local axis. So I explained the concept of local axis and global axis in my webinar 1. So if you have some doubts, go to webinar 1, you'll understand what is local axis and global axis. I'll just show you the difference between, what if I change my beta angles? Okay, I'm just select, I'm just selecting bottom 4 members to show the beta angles. Okay, we have selected this 4 member. We will go to render view. You could see in their top view, they are aligned properly, so that all angle faces they are to the external side, so that it will be ease for the construction. This is how the ideal arrangement should be. So is that every 90-degree angle is facing inwards and all the faces are towards outer side. But what if I change the beta angle of some member? Say I am changing the beta angle of this member. Change beta. I'm putting it as 90 degrees. So it will rotate anti-clockwise. You could see the difference click on OK, close. Now again I will select those four same members and we'll go to rendered view. You can you see the difference here? You know, this particular member here. Can you see the difference here? Initially it was facing inwards, now it has been rotated through 90 degrees. So we don't want this kind of geometry, we want the previous ideal geometry. So we'll again go to general and I will again double click on that and I will change beta angle to 0 degrees. Click OK, close. Again we will check the orientation of this. Okay, now you can see this. This is towards, facing towards, I'll just zoom it up, facing towards y-axis. Great. Okay, so we're done with the general tab. We have signed particularly sections. We have checked what is beta angle also. Now we'll go to loads and definitions. In loads and definitions, we'll define two load cases. One will be self weight, and another will be a simplified format of a wind load. Basically, wind load acts on all the members from windward face as well as leeward face. We are just going to consider windward face. And that windward face also, I have calculated the wind forces which will act at a node. Basically it will act first as a act on a panel, then it will get distributed on the members, and then finally it will act on a node. So I have simplified that for you people. I have calculated all those and I'm just going to apply it. So go to load case, add load case, click on add second load case also, close. In first load case, click on add, say self-weight negative y direction. You know how to do it. Click on add. Go to load case 2. Okay, go to load case 2, say add. Now we are going to add nodal loads to load case 2. But there will be 3 nodal loads. I'll show you. Exactly. No, I'm just defining. Just follow me. Follow my procedures. I'm defining it as 20 kilonewtons. It will be 15 kilonewtons. It will be 5 kilonewtons. Okay, I'll just change it. No. I don't want any direction in Fy. I'm just rotating it. Great. Add. Okay. No, there should be 0, obviously. I'm just adding force of 20 kilonewtons along x direction. No, I will add only 10 kilonewtons. Wait a minute. Or I will go with, no, wait. 15. I will go with 15 kilonewtons. Click add. Then again, I will go with 20 kilonewtons. Click add. Then again, at the end, I will go with 5 kilonewtons. Click add. We are going to assign these particular loads to the nodes. So we are going to assign 15 kilonewtons to this top intersection node. I'll show you how. I selected this. Now I go to node cursor. I'm going to apply to this node. Say assign to selected nodes. Click on assign. Yes. So the force is already applied. Now I'll apply 20 kilonewtons to this particular node. Where it is, Okay, in this view I can do that. So basically I'm applied 15 kilonewtons at 0, 12, 0. Now I'm applying 20 kilonewtons at 0, 9, 0. Sign. Done. Now I'm going to apply this 5 kilonewtons at 0, Okay. No, it was firstly 15 kilonewtons at 0, 12, 0, 20 kilonewtons at 0, 8, 0. Now I'm going to apply 5 kilonewtons at 0, 4, 0. Again, I will check. Okay, this is node 18, node 20. Assign. Done. So I assigned 3 nodal loads which will act as a wind forces. And before that, I will assign the sulfate. Say assign to view. Assign. Great. So sulfate is also added. Great. So sulfate is added, wind force is added. Now we can go to analyze and print. Oh, no, before going to analyze, we forgot to mention something. In general, there is a tab called material. And go to steel, say edit. So for today's computation, these values which you are seeing on the current window should be your ideal values, and you could only use this particular steel of this yield stress, tensile strength, all those ratios, shear modulus, density, modulus of velocity, etc. You are not allowed to change these factors. So please keep in mind. Cancel. If you change any of the factors, you'll be disqualified. Okay, and now we can go to analysis and print all, say all, click on add, close. Now go to analyze and analysis, save. Okay, it has shown some 2 errors. We'll check the errors in a minute. Support. Okay. So can you tell me why we got this error? Because we haven't added the supports. It's fine. We'll do it again. Don't worry. We'll go to general, support, create support. I'm adding fixed support. So I'm going to add fixed supports at the bottoms only. But not at this. No, wait. I want fixed supports at all bottoms except origin. I'm deselecting the origin. Great. So assign to selected nodes. Wait, again I need to select. Okay, great. Assign to selected nodes and click on assign. Yes, great. Now we'll go to analysis, print all, say all, add, close, then again analyze and analysis, save. Okay, so now we have 0 errors, 9 warnings. So we'll first go to the post-processing mode. Oh, before going to the post-processing mode, we have just created load cases, but not load combinations. So still now, we are only focused on load cases. So we will again go back in modeling, in general, loads and definition. We'll see the load cases. So click on load case details, click on add, say define load combination. I want load combination as load case 1 plus load case 2. So load case 1, enter into this, load case 2, click on add. Done. So again, I have to go and print all analysis, click on add, close, say analyze, run analysis, save. And now I have 10 warnings. I will go to post-processing mode, click on apply, okay. So this is the post-processing mode in which you can see here, I'm selecting this particular node. So this is the top node you're seeing. In top node we have 0 mm deflection with respect to load case 1, 0 load case 2. And with respect to combination of 1 and 2, we have 7.451 mm deflection. So is it allowed? Obviously it is allowed. This is a 12-meter structure. So basically it will be 12 meter by 500. So h by 500 is the allowable deflection. So I will just show you what is 12 by 500. Calculator, I'm opening my calculator app. So 12 divided by 500. So this is 0.024 meters. So I'm multiplying this by 1000. So allowable deflection is 24 mm only, which is 2.4 centimeters. Did you got my point? 24 mm. So this is the deflection 7.45 mm. This is in limit. So allowable limit is 24 mm for this. So this is okay with respect to deflection. But we are not seeing the deflection, so we'll change the scale, labels, go to scales, we're increasing the scale. Okay, so now you can see the deflection. Great. And now you know how to check stresses, etc. Everything, you know everything, right? I don't need to teach you all these things because you know how to go about stresses. See, we have defined this as a truss member, so you could see there's no bending moment or shear force in this member. So this is the advantage of defining this entire structure as a truss structure. So again, we will go to animation. You would like to see some animation? Great. So this is the animation. This is what's happening after the application of wind force. Basically, it's a application of lateral force. Great. Again, we'll go to modeling. Now we'll design our structure. So go to design. Put some commands, design commands. Before doing the design commands, make sure you have selected Indian code, which is IS 800 2007 limit state. Great. So I selected Indian code. Now put in commands. Say check code, add. Member takeoff, add. Select, add. We are not adding select optimize till now. We'll do it later. Take off, add, close. So we added 3 check code, still member take off, and select and still take off, right? Now we will define some parameters. We want, click on define parameter, you will come to this window. In this window, we want kx, ky, kz. So right now it's putting, I have put it as 1, that's fine. But you could add it, click on add, ky, add, kz, add. These are basically k values, different values with respect to z axis, various axes, right? Now we'll go to main. I want slenderness ratio to be 180. Click on add. Just check whether it's added or not. Yes, it is added. Again, go to define parameters and search for FYLD. FYLD, okay. So we are using a steel of grade Fe250, so that's fine. 250, 250 MPa basically. So you could click on add, close. So these are the parameters you need to add. And again, go to check code, assign to view, assign. Go to steel member takeoff, assign to view, assign. Great. Select, assign to view, assign. Again, kx, assign to view, assign. ky, assign to view, assign. Oh, we have changed something. Okay, we are assigning ky. Click on assign. Yes. kz, assign to view, assign. Main, we want slender ratio to be 180. Assign. Great. FYLD, assign to view, assign. Great. So we assigned everything. Now you know what to do. Run analysis. Yes. So it will design every members. It's designing all the members. Wait for a minute. So 0 errors, 28 warnings. View output file. Done. So there are some factors. Let it be. We're going to results. In steel design, you could see in member 1, particularly member 1, there is no force as such. So this is basically a zero force member. So that's why you could see here all is pass and the utility ratio is 0. .95. As you go on increasing the section, you could see here in member 7 particularly, we'll go to member 7. What section we have assigned is 65 by 65 by 10, which is showing a utility ratio of 0.023. Critical load is case is 3. And if you go to steel takeoff value, it will show you 15.049. In this select steel design, it is suggesting of 60, no, wait, number 7. It is suggesting 30 by 30 by 3, and which increases its utility ratio also. So in this particular select design command, you could see the ratio has been increased to 0.458. Still, we need to reassign this stuff. Again, we will go to this steel design. You could see here, member 7. I initially assigned 65 by 65 by 10. Are you getting one point? Great. When you assign 65 by 65 by 10, you just got 0.023, which is the critical ratio. Every member is pass. Okay, we could search things, fail. Fail. Okay, there is one member who have failed. So, which is that member? Member number 10. It was suggested 65 by 65 by 10, but it got the force of 1.805. So all those members from member 10 are failed. Some due to slenderness, some due to critical ratio, etc. Now we'll go to steel design. Again, I will go to member 10. They have assigned a section of 120 by 120 by 8, which is giving a utility ratio much lesser, but it is not slender. So what we need to do is, we will increase the utility ratios of member 9, member 10, member 11, something like that. We'll do it. So first we need to know which is the member 10. Okay, this is the member 10. See, this is the quite slender section, right? And this one is number 31. Again, you will go to output file. You will see in the results. You will go for number 31. Is it passed or failed? Okay, number 31 is also failed. So we need to reassign. Firstly, what we'll do is we'll create a geometry again. Okay. Now we are creating a brace frame. As you can see here, we are creating a base frame by simple methods. We can do these things by translational repeat also, or rotational repeat, but it will be a little difficult right now. So I'm doing it manually. just creating a braced frame structure. Wait a minute, I'm just finishing up my structure. I think we are finished. Great. So again, we'll go to general. Obviously, there are a lot of properties available, but we'll assign this to assign to view, assign. So yes, initial property which we have selected. Let's see the ended view. Everything is assigned. Rest of the things the same. So now we can analyze again. So this time the scenario will be much different, little different. We'll first go to post-processing mode. Okay, you could see here. Initially maximum deflection was 7 point something, so it has been reduced to 4 point something mm. So the reflection has been reduced. Now we'll see the output file. We'll go on searching fail, find next. Okay, still member 10 is failing. I think it does not consider the commands. Wait. And we'll go to analysis and say add, close, commands, analysis, save. So again it is designing the members again. Total steel takeoff parameter is not defined, I think. Oh, okay, we'll assign this parameter particularly. Wait. We'll assign this total steel takeoff to view. Great. Again reanalyze the structure. Okay, it will take, is taking some time. Now we'll look for this second steel design. I think we need to put the command also again. Fuel design, commands, check code, add. Remember takeoff, add, select, add, takeoff, add, close. So check code, assign to view, assign, say yes. Still remember takeoff, assign to view, say yes. We are applying these commands again because we have changed the geometry. Yes, still take off, assign to view. Yes, great. Now we could go to analyze and analysis, save. Yes. Now we will see the output file. It will be much better. You could see the differences. It's still designing these sections. The warnings has been increased. Don't worry about the warnings. Those are fine. And this, remember number 1, 2, 3, 4. Those are basically horizontal members. They are not getting any load. So you could just delete these numbers. Now, initially, it was failing. We'll go to this still design. So, member 10, ratio is 0.056, critical section. Okay, load case 3. So, what we have assigned to that section is, wait a minute, this was an initial design. We assigned 65 by 65 by 10. So it is failing and giving utility ratio as 1.805. And in the final stuff, it is showing member number 10, 120 by 120 by 8, and showing the ratio, utility ratio 0.114. So we need to go for lower section. So we are closing this. We'll go to general. Is there any lower section available? 120 by 120 by 8 and between 65 by 60. Okay, there is 190 by 90 by 6. So we'll assign this. Wait a minute. Before I need to know where is member 10. Okay, this is member 10 particularly, right? General. Okay, member 10 is already selected. I'm selecting the properties. Wait, I am filling these. Okay, I selected the member 10. No, wait, I'm selecting the member 10. Okay, member 10 is selected. Now I'm assigning this property. Assign, yes. Now we'll analyze again. Just focus on the member 10. That's it. It will take some time to reanalyze the structure and redesign it. Okay, go to output file. Done. We're just going to focus on. They suggested 120 by 120 by 8 still. And what we have applied is number 10. You could see here. Still 90 by 90 by 8 is also not enough and it's giving a utility ratio of 1.268. So we will assign a bigger section again. Again, close it up. Is there any bigger section? 120, 90 by 90 by 6. So we need a section between 120 by 120 by 8. Where is the section? Okay, we will assign a, go to section database. But can you see that? It was initially 1.835 and now utility ratio is decreased to 1.128. Now we will go to again Indian, go to angle sections. We'll get a bigger section. Wait a minute. We'll get a section of 100 by 65 by 10. Add. So the section is added, member beam is selected and say assign. Say yes, yes. Analyze, run analysis, save. It will take some time to reanalyze the structure and redesign it. So basically whatever we are doing right now is the iterative design process to optimize the sections. It will give you number of warnings, don't worry about the warnings. There are just warnings regarding codal provisions. You can rectify them, don't worry. Go to results, first field design, go to member number 10. Okay, so we have decreased, somehow decreased the area. So that's why it became 100 and 1.624. So we need to go for still higher section. So again I'm closing it. We'll go to this section. Where is this section? Higher section. 100 by 150 by 15 by 8. No? Okay. I'm selecting the member again. Number 10 is selected and say assign. Yes. Go to analyze, reanalyze. Great. Say yes. It will take some time. So this is the procedure. You need to do it again and again for most of the sections till you get an optimized geometry. As soon as you come up with the most optimized geometry, your warnings will be reduced. Don't worry about that. Warnings will be reduced. I'm going to member 10. Okay, you could see here. Now it's pass and but showing a utility ratio of 0.066. So it is drastically reduced. So we need to go for somewhere, somewhere in between 100 by 50 by something. So again, we'll try to reassign something. We will check the area. So this was that now. So if you just consider 100 by 60 by 10, 65 by 10, what is the area of that? 100 by 65 by 10 view table. I'm just want to see 100 by 65 by 10. Hundred by 65 by 10. So I will look into this. This is the area 15.5, and the section we assigned is 150 by 115 by 8. So 150 by 115, 150 by 115 by 8. Okay, what is the area of this? 24.9. So we need to go somewhere between 24.9 to initially it was 15 point something. So we'll decrease, again. We'll see that section 100 by 65 by 10 again. 100 by 65. 100 by 65 by 10. Okay, so what's the area? 13 point something, no, 15 point something. So we'll assign a section of this area, maybe 16 point something area, which is 100 by 75 by 10. Again, we go to this. 15 point something, no, 16 point something area. Or what we could do is, we'll assign this section of 17.10 area, which is 100 by 100 by 110 by 110 by 8. So we'll go to 110 by 110 by 8. We are just changing the section. Make sure you understand these things. Change. Yes. Close. So select this section. Now select our member number 10 again. Great. Say assign. Yes. Analyze, analysis, save. It's redesigning. It will take some time. I hope you are getting the process. What we are doing is we are trying to get utility ratio as close as to 1. I hope, or you obviously know, I assume that you know what does it mean by utility ratio. Utility ratio is basically ratio of the design force on that particular member to the strength of the member. Done. I want to see the output file result, and that will go for design first. Okay, see, it's between 1.040. So we just need to increase the area a little bit, then it won't fail, it will pass. So we will go to it again. Now we will just change this section. So 110 by 110, we go to view table. 110 by 110. 110 by 110 by 8. This was it. So the area was 17 point something. So we'll looking for an area of 18 point something. Okay, I think this will be fine. 18.8. That will be much different actually. Just slight increase, you can get something. 17 point. No, go up. It was 17.1. So we need a slightly bigger area than 17.1. Can you find something similar? Okay, we will go with this section, 17.5. How about this? I say 150 by 75 by 8. Great. Assign the section. Again, I'm going to run analysis. Save. Say I want to proceed. Now it's redesigning again. This is very, little tiresome task, but it is the fun part actually. It will give you an overview how to design things because this is what happens. Go to output file. I think it should have been passed till now. Go to this for it is design. Yes. No. The section hasn't been assigned properly, I think. We need to go back and assign the section again. Okay, the section didn't got changed. 110 by. It should have been 175 something, right? Okay, we'll go to it again. View table. We want something related to 17 point something, right? We want areas near to greater than 17 point something. We're searching for area nearer to 17 point something. This is it. Okay, so now I have added 150 by 75 8 and I selected this member and I'm assigning it. Say yes. Great. So the section is also assigned now. I will go to analyze, run analysis, save. I think this time the section is assigned. Last time there was some error, so section was not assigned. It's fine. It's okay. Things like this happens. Don't worry about it. It will take again some time. I hope you are with me till now. So we are just optimizing one section. There is a lot to optimize. Okay, go to results, to design. Yeah, you could see here. It's still failing. It's a ratio of 1.393. So we need to have a bigger section still. See, what happens is when we add, particular type of loading to it, so it adds to sulfate also. We need to take care of sulfate also. So we will apply a bigger load, a bigger section, and we'll pass it. Don't worry. This time we'll do it. We're searching for something between 19 something. Search for 19 point something area. Search for 19. Okay, we got something. 19.20. Okay, 120 by 80 by 10. I'm putting 120 by 80 by 10. Great, I think. Select. Sign. Yes. I selected a member as well as geometry and assign. Yes. I'm reanalyzing the structure. I hope this time it will pass. Hopefully. Or we need to go with a higher section. Don't worry. Our job is to reduce that utility ratio and bring it to as close as to 1 as possible. Number 10. Oh, it's still failing by some ratios. So we'll put up a bigger section. I think this section will be far bigger for that. Same. assign to selected members. Analyze, run analysis, save. Yes, it will take some time for analysis. So this process will go on till you get your section to be optimized and your utility ratio as closest to 1. But there is always a way. I have already taught you something called select optimize command. Go to still design. Check. This time it's passed, but the utility ratio is decreased drastically. So that there is a lot of difference between areas. So we need to cover up these areas, use some more sections, so we'll get a better thing. Or we could do is close this, go to design, add a command, select optimized, add, close. Where is this optimized command is added? Okay, is it added or not? Select optimize, okay. So it's given already. It's assigned. So analyze, run analysis, save. We're doing it for the final time. Staad will give you the optimized section according to all the selected parameters. So wait for this final analysis. So this is how you need to play with the Staad. First you need to play with the sections, then you will play with the geometries, etc. So this is the fun part. So enjoy this journey. It's taking some time. Wait for it. And don't worry about the warnings. They will get reduced. Until and unless you have some errors, don't worry about it. You can see here still design. And still that it will be 0.036 and it will in this still design come here. It has shown the 120 by 120 by 8 and the utility ratio has to be 0.11 for load case 3. Again, I will show you. These are the iterations Staad has done, showing 120 by 120 by 8. So this is the optimum section. Great. So you could have optimum section set in one command also. But you might have a question. Why the utility ratio is so low then if it is optimized section? Because of some other criteria like slenderness ratios and all that. Okay, this is showing some errors with respect to. So what you need to do is if your slender utility ratio is still not coming to the 1, you need to redesign your geometry. So basically you need to decrease the length of the members so the slenderness ratio will not increase. You can do this by dividing the beams into 2 parts, adding some more beams. So play on. This is the competition. So the one who will come up with the best possible design, which will be most optimized section. At the same time, how will you choose the optimum section? Simple. Loading condition, everything is same for all. So the one thing which will make difference is this takeoff value. I will show you the takeoff value. Steel takeoff value. So this will be final takeoff value 31.851, considering all members are none of the members has failed. So by this value we are going to judge, because it doesn't matter if the section is optimum, nothing. It's a first thing, your section should be safe, and the second thing, most important thing of structure, it should be economical. So about the economy, if you can achieve the economy, so you need to have less material cost. So for less material cost, you need to have less self weight of the structure. So keep these all things in mind. Practice a lot. This is the fun game. Once I give you the problem statement, you have 12 to 15 hours to solve and decode the problem statement, come up with the best possible design, use your theory, do anything, whatever you want, just come up with the best possible design. So all the best for the competition. I hope you'll come up with some nicely designed geometries as well as structures. So let's see how you can do it. And before going further, I will explain something about loading. In loading, we have created those loading on the central axis. So make sure in your structure also you have y-axis as a central axis. That's it. I'm signing off. I'm Shrenik Bora, technical event head of the event Bob the Builder 2.0 from Nirmiti. So I'm signing off. So this is the last words you're hearing from me regarding the competition, training, stat, anything. If you still have doubts, feel free to ask. We'll still support you. Don't worry about anything. This is the fun game. Just play a lot. You'll definitely win. That's it. There'll be some other instructions regarding. You'll be given a brochure. Other instructions will be given on the Facebook page. So don't forget to follow our Facebook page. Follow us on FB, Insta, Twitter, everything. That's it. So all the best for the competition. Thank you.